The class that I'm going to do today is perhaps going to be very difficult, or perhaps not. But I want to give you some inspiration, and I was thinking how to put it in context. And so I imagine you're now, we're approaching the medium part of the term. You're probably surrounded by assignments and maybe midterm exams, and at the same time, for some of you, this is the last few weeks before you graduate. You may be looking for jobs, so your life must be very intense right now. And then here I am. I'm going to give you a lecture today, which I think is going to be, it could be difficult, but I want to give you some inspiration. And I wanted to mention to you the history or the story of Hercules. I'm not sure if you're familiar with Greek mythology, but I want you to feel a little bit like Hercules. Hercules is this myth of this person who was infinitely powerful. But in fact, if you look into the mythology, his power was not really just innate. He didn't have it. He developed it. And he developed it in times of uncertainty. As you may know, he was given some impossible tasks. He was given the task of killing a lion whose sword could penetrate. But then he learned that if he fought the lion, he would use his own nails to kill him. Okay. Then he was asked to find these miracle apples, and then what he did is he just got help from other people to help him find them. He was asked to fight Hydra, the serpent whose head reproduces into two every time you cut it. So then he got someone to cauterate the head as soon as he cut it. So he got people to collaborate with him. It's a very nice myth that could help you in times of difficulty, because you can see how getting help from other people and sometimes thinking about the problem in a different way can be of assistance. And if you're not very familiar with Greek mythology, if you're familiar with the similar stories in Chinese culture. In fact, the Chinese culture has this nice 5-element philosophy that talks about transformation. So this could be very helpful. And I wanted you to be aware of this as I'm about to give a class which is a bit of a pinnacle when it comes to mathematical finance. And I want you to feel energized, despite the fact that I am aware that some of the things that I will do today, some people will not understand. And I'm telling you, if you don't understand these things, it's really not a very big deal. It's not that the things that we need to learn today are really optional. You're going to encounter some of these things in your professional life. But today I would encourage you to take what you understand with you and just make a note of the things that you don't understand. Normally I tell you, you have to understand everything. You know how much I insist that we're all together as we climb these hills of knowledge, and every day we'll learn new things. And I like to wait for you. Today I understand that some people may decide to just stay behind, and that's okay. We'll catch you up on the way down. It's no problem, okay? But just make a note of those mountains that you feel that you cannot climb today. And I do that because, as I've mentioned, this course that I'm teaching is really a huge summary of many other things. And I find this to be the optimal way for you to learn what we're doing. So in preparation for that, what I'm going to do is I'm going to start with the episode we already saw. Last week, I remember I divided all of the elements into episodes, and we finished with episode 7. I'm going to start with episode 7 today because many courses start this way, and which of course I don't like. I like to do it the way we did it last week, where I developed a 33-cent game, and then with that game we learned a very practical approach to what we do. and we developed different ways of thinking about pricing, and we developed the concept of replicating portfolios and really many other things. Once we have that knowledge, once we know what we learned last week, then I know I can talk about the capital asset pricing theory, and I know I can talk about the dynamic asset pricing theory, both of them, with certainty that you understand what I'm talking about because you know the 33-cent game. Now, many courses don't do that. They just go directly into the theory, and then everything else is a consequence, but that's not the way I like to do that. So we developed this formalism in class last week where we consider the event space. These are the things that might happen. We already went through in our 33-cent example. The event space was the stock going up, the stock going down, only two. Okay, the simplest non-trivial example we could find. If we had three stocks, then, two stocks, then we could consider four elements. Two stocks go up, two stocks go down, or up, down, down, up, right? And that will be our event space. And you can think that with this mathematical formalism, we can really describe really anything. And we've seen examples of all of that. So this is our probabilistic approach to what we did, which is now going to be very formal. And by the way, this could be extended to infinitely many individual events. We could extend this to infinite probability spaces, but I'm not going to do that. It could be done. And I would mention sigma algebras and all that, but I'm not going to do that. Except I'm going to mention to you that if at some point in your life you need to do this from a sigma algebra perspective, perhaps because you're doing a PhD on this or something like that, then what you've learned here will be incredibly helpful, because the formalism is the same, and mathematics has been built so that whether you're dealing with a finite or infinite probability space, most statements are really the same. Okay? And then the financial, that was just probability. Now the financial aspect of this, how the randomness interacts with financial markets, was given through securities. Now these are securities that have a certain future value that we know in probability. So under every one of the events that might happen, we know what they are worth. That's what these securities are. And we represent this with a matrix that we call the Pij, where I represents a security and J represents an event. You can organize this information as a spreadsheet. You can organize the information as a matrix. And as we will see, as I mentioned, the matrix approach will be convenient not only because it helps us organize the information, will be important because the matrix, with its arithmetic properties, would help us build the replicating portfolio and the price. So you see, it's not just that we organize the information as a matrix, is that because we organize the information as this particular matrix algebra, computational algebra, will make the calculation of what we're doing simple. Okay? And we usually adopt the terminology that the security S naught is the bond. The bond has the characteristic that is deterministic. It's the only security which is deterministic, and it has the same payout, say 1, under every one of the possible scenarios that might occur. And we call this the payout matrix. These securities all have costs. As you know, some securities have prices, costs, which are given by the markets, and others don't. So the ones that have a cost are the ones that we're talking about here. So in the context of your assignment number 1, this would be the bonds. These are your securities, and they all have costs because they have prices that you obtain from the website. Zero coupon bonds, for example, will not be here because they don't have published prices. Only those bonds could mature in less than 6 months. Those will be the only zero coupon bonds that will be part of our securities page. You understand what I'm saying? So these are the securities whose prices we know. Of course, our interest is in the securities whose prices we don't know. Last week was the 33-cent gain, but in your assignment, the securities whose prices we don't know are the zero coupon bonds. You see, it's the same game. And the formalism that I'm going to develop today will work both for your assignment number 1 as well as for the derivative pricing that we developed last week. And of course, for many other things too, as you can imagine. All right. So then our setup assumes that we have financial instruments and events that might happen. And the payout, and there is a payout matrix and a cost vector. This is the information that's given to us. And this is how we approach the task of understanding financial markets. From the capital asset pricing theory, that is the information that we want to have today. The result is going to be that for those other instruments whose costs we don't know, but a linear combination of the securities whose prices we do know, what we call a derivative, we will see that if the payout is in the linear span, then of course we can solve it easily because there will be a replicating portfolio. And if the derivative is not in the linear span, then, well, we don't know what to do because there is no price, there is no replicating portfolio. Okay? Again, we saw that last week, and now this is going to become a formal definition. So, back to our game. The payout matrix is 1, 1, 2, 1/2. 1, 1 because the first security, the bond, will always be worth 1 whether the stock goes up and down. And the stock will be worth 2 or 1/2 because if it goes up, it's 2, and if it goes to 1/2, and if it goes down, it's 2 1/2. So that payout matrix gives us the information we need about the future behavior of these securities. The cost is 1, 1 if we assume there's no interest rates. That's how we can express our 33-cent gain with this formalism that I'm developing today. It so happens that the span of the columns of the payout matrix is all of the R2. That means that we're dealing with a complete market. That means that there's always a replicating portfolio. Okay, so I'm just giving you the mathematical formalism of what we already did last week. In the situation where a stock worth $1 could go up to $2, stay flat, or go down to 50 cents, independent of the probabilities, the payout matrix is going to be this one, 1, 1, 1 for the bond, and 2, 1 or 1/2 for the stock. That's the payout matrix. That's the information that captures the information we have about the financial market. And there what we notice is that the cost vector is the price of the bond, 1 if there are 0 interest rates or some other number otherwise. And with this situation, we know it's an incomplete market because we know that the span of the columns of the payout matrix is not all of R3. We know that. R3 because we have we have a 3-dimensional probability space. And that means that there could be payouts like this one, which are not in the linear span of the columns of the matrix, that cannot be priced. And we saw this last week. But then, if someone, I believe it was Henry, offers $0.33 for this particular security, then the information we have about the financial sector changes, because now we have a new security with a new price, and that's what liquidity providers do. That's what many banks do, who act as brokers. That's what brokers do. Now, suddenly, because of this change in the market, someone is offering me a new price, then my payout matrix will change to this. And now I'm in luck because there's a cost vector associated with that. And as you see, this is the cost vector includes the 33 cents that someone was willing to offer for that option. And when you do that, then now everything changes, because my matrix, my payout matrix, the columns of it will generate the entire payout space. So I will always have a unique price for any payout that's given to me. And if, for example, someone comes up with a different option, this one here that pays you 20 cents if the stock drops to 50 cents, then this option can be written as the linear combination of the securities, because the securities payout spans R3. So we know that this exists, and the solution, of course, will be the solution to some system of equations, because that's how you find the linear combination of vectors in the vector space that we're dealing with. You've seen that in algebra many times. And not only this, but all payouts can be priced, and replicating portfolios will exist. Replicating portfolios will be the solution to the system that asks for the linear combination of these payouts to give me 0, 0.2. Okay? That's what we saw. And this starts to look more and more and more like linear algebra, the type of linear algebra that you have seen many years ago. And of course, linear algebra will be the key to solving this in a very organized manner. We just need to organize the information properly, and then computational algebra will give us the solution. So this is not hard. This will be easy. And this leads to what I call the general method for pricing and replicating. And again, we did this last week. I remind you that if I have now my market with any instruments S sub I with a certain payout matrix and a certain cost vector, if I have a different security with a payout given by some combinations, then the replicating portfolio is that one that if I multiply the payout matrix by the replicating portfolio transposed, then I get my payout. By the way, this is how we found it in last week, the solution for our replicating portfolio, which was I'm going to borrow 33 cents from my bank. I believe Muscan was my bank, and then I bought 2/3 of the stock from the broker, and then I go home and wait. Tomorrow I'll have exactly the amount of money I need to pay the payout of the option. That's exactly what we're doing here, but we're writing it in matricial form. It's exactly the same. It's exactly the same. The replicating portfolio, therefore, can be written algebraically as the multiplication of P inverse times the payout of the derivative. So there you go. I have a mathematical closed form expression that works in any space of any dimension, with any securities and any replicate in any event space. This is how it always works. Okay? And if that's a replicating portfolio, what's the price? The price is the product of the replicating portfolio times the cost vector, because that's how much the cost vector, because that's how much the replicating portfolio will cost. So what you have in front of your eyes now is the mathematical expression of everything that we did last week. It encapsulates the information of my market in the matrix P. It encapsulates the derivative, the nature of my derivative, in the vector nu, which contains what my game will pay as a function of the different things that might happen. It encapsulates the cost vector, the cost of each security, which for us last week was $1 for a bond and $1 for a stock. And then with that information organized that way, the matrices not only capture the information, they give us this arithmetic property that the replicating portfolio is the result of a matrix multiplication, and the price is the result of another matrix multiplication. As you can imagine, you can program this in a computer, and then you just find a way to get your market information, and then boom, you get the answer to that. Let me pause here for a minute, okay? I suspect you're still all with me. This is what we did last week, and in fact, this slide was covered last week. There's two perspectives on this that I want to convince you they are the same. I don't want to prove to you they are the same. I'm not interested in proofs. I'm not interested in that proof. I'm interested in conviction. This applies to your 33-cent game that we viewed last week, but it also applies to your assignment number 1. You didn't follow this approach in assignment number 1, but you follow another similar approach where you're essentially solving for the price of zero coupon bonds from the price of coupon bearing bonds. It's different because this is a one-period model. You're dealing with a multi-period model because you get cash flows at different points in time. But you probably sense that there is some relationship, right, between what I'm doing here, expressed this way, and what you did in assignment number 1. Oh, sorry, on what you are doing in assignment number 1. You're still working on it. So that relationship is not a coincidence, and there is a theorem, the fundamental theorem of asset pricing, which actually tells us in very abstract form that yes, this and your assignment number 1 are actually the same thing. Okay? So this is that connection which I just want you to now visualize. I don't need to prove it. I don't want you to even fully understand it. I just need you to visualize it. So let me make a comment about this expression. And this is a comment which is going to point to your intuition. This is how I want your intuition about this to be. So the price of my derivative expressed at this matricial product is the product of one matrix and two vectors, one on the right, one on the left. So let's think of that as follows. The price of my matrix times the cost vector, I'm going to focus on that. That is going to give me some vector, P1, P2, P3, Pn. It's going to have some components there, whatever they are. Right? So this is interesting because that means that the price of my derivative is going to be the product of the payout times some numbers. Right? So if these numbers would add up to 1, then they would represent probabilities. And then I'm telling you that you can price the derivative taking expectations, because then this would become an expectation according to a probability given by the magical numbers P1, P2, Pn that we obtain by multiplying the cost vector times the inverse of the payout matrix. See, the advantage of having the camera on is I can see your faces and I can see who understands and who doesn't. So I have a pretty good view, I have a pretty good feeling that I think you understand what I'm talking about. But now here's my question. Is it true that P1 plus Pn is equal to 1? If it was equal to 1, then I would say that we found the risk neutral measure, because that's what the risk neutral measure was. If it's not equal to 1, then I would say, what is it? You understand the question? And I know that now I'm dealing with, abstract considerations and hypotheticals. I understand that. But I think that you probably understand what I'm talking about. So if this was equal to 1, then I could say the price of a derivative is the expected payoff. And this would be the expectations. This is the measure space that would price my derivative if they are equal to 1. Yes? And then this would be the risk neutral measure, which is what we defined last week. It's the measure that prices the bond taking expectations that we saw is not the right approach to calculating prices. But where are they? Consider the bond. Let's apply this formula to the bond. The bond has the bond is not a derivative, but has some has a payout. So if I apply this to the bond which is the security that has a payout equal to 1 under every scenario, what happens? What happens is that I get that the sum of all of the components of that vector is equal to the price of the bond. So if interest rates are 0, then this is a probability space and this is an expectation. That's what this says. But if interest rates are not 0, this is not an expectation. This is what we call an expected discounted payoff. In other words, there still is an expectation, and that's the risk neutral measure. But it's not exactly those numbers P. Those numbers P will have both the expectation and the discounting built into it. In other words, those numbers P are a blend of a mathematical object and a financial object. Very easy to decouple, because I just need to divide each of them by the price of the bond, and then I have an expectation. And that will be the risk neutral measure. I hope I didn't lose you. I suspect that you understand what I'm talking about. I hope you see that there's something very interesting here that perhaps you would like to understand very well. Okay? But I'm not going to spend time on this just yet, because I'm going to give you an even better way of thinking about all of these things. But now I hope that at least intuitively a lot of these elements are coming together. Yes? And we begin to see how powerful it is, this theory that we're developing here, because it helps us solve the simple problem we were dealing with last week. But it looks like it has like infinite potential. Because what it tells me is that if I organize my information correctly, I don't care how many securities I'm dealing with. Computers can deal with very large matrices. Then you can price everything. And then you're in control. You can actually monitor the financial markets with this. And that's what I want to do. Okay? Now, to do that, I'm going to adopt an even more abstract perspective on financial markets, even more abstract. And in fact, I'm going to state and prove to you the fundamental theorem of asset pricing. Now, this is going to suddenly, the next half hour is going to look very much like a math class. For those of you who will understand it, wonderful. If you don't understand it, I would say don't get stressed out. If one day you need to understand it, I can guarantee you, you will be able to understand it. It may take more time. Okay? In normal courses in math finance, this is done properly with a lot of detail, which I'm not going to do. I'm going to explain this to you as fast as I can, maybe half an hour, just so you see the landscape from here. We're not going to climb this mountain. We're only going to look at this mountain from the other mountain we climbed earlier. My interest is that you have some view of what this looks like. I don't need you to understand all the details, okay? That's my decision. All right, so how do we approach this? We approach this by taking an even more abstract approach to finance, and I consider a securities universe, which are securities with costs, with prices. I'm going to assume there are a finite number of them. My notation is going to be that way, but I could also assume that there are an infinite number of them. I'll try to be careful and tell you what the assumption should be if I have an infinite number of securities. Now, a portfolio is going to be a vector that represents the weights in each of those securities, and it's a vector in Rn because I have n securities. If I have infinitely many securities, then a portfolio is going to be a vector which is going to be in the space L1 of Rn. In other words, it's a function that has, usually we assume they're in L2. If you don't know what I mean by L2, don't just ignore it, okay? Usually I assume that they are in L2. Why? Because there's going to be a natural Hilbert space structure in what we're building here. Although with L2, we could have portfolios that cost an infinite amount of money. L1 will give us a finite amount of money. We're not going to get concerned with that. So a portfolio is just a vector in Rn. That's going to be the case. If we have infinitely many securities, we will want the portfolios to be of finite cost, which means that the sum of the components is less than infinity. We don't want to deal with infinite amount of money. But for most of you, you don't want to hear this. Security, each security we'll integrate has a payoff and a cost. And now the payoff will be a random variable. All those values that could have, we're going to think of each of them as a random variable. They are a vector, I understand, but a vector is also a random variable on a probability space that contains those as the events. I'm only changing the notation. I'm not talking about anything different. Okay? It's a random variable. And then every event in my event space represents the possible outcomes in a probability space. And there's a measure, maybe there's even a sigma algebra if it's of infinite size. Not concerned with that. We understand this now. And we talk about a payout matrix when we deal with finitely many securities. If we're dealing with infinitely many securities, then it won't be a matrix, it will be an operator. For those of you who know what an operator is. Then the payoff is a random variable, and we consider random variables who are square integrable. If we're dealing with finite ones, then we don't care. They're always like that. But if they're infinite, for those of you who may care about extending this to infinite dimensional spaces, they need to be in L2. Okay? If you don't care about infinite, just ignore this statement. Then markers will be complete when the span of all of these random variables is all of L2. Or if you're dealing with finite dimensions, the marker will be complete when the span of all these payouts is the entire Euclidean space. We already saw that. If you don't understand this, then please delete it from your mind and just remember the one that I gave you about 20 minutes ago. Okay, so someone is asking what is the L2 space, Daniel. The L2 space is the space of square integrable functions. Let me go back to the previous slide. So what you see here, again, this is now a course in functional analysis. This is not finance anymore, okay? Today we're going to be dealing with a lot of the things that some of you with advanced math may know. So this is what's called L1. That's a one, a very bad one, L1. L1 means what? Means that if I sum these things to the power 1, it's finite. If I sum these things to the power 2, then it will be called L2. Okay? And though some of you may know a lot of math, and you may know that if you raise this to some other power, and people sometimes write this as P, then it's LP. And I'm sure in some course in calculus, sometimes someone introduced this notation because they like to consider functions which are square integrable or whose integral who have a finite integral and this and that. Sometimes this notation is developed as early as in calculus. Okay, you may have seen that. But this is something which is, if you're not concerned with this is not a problem. Okay, I'm just going to give you a hint of how some of these things get to be very sophisticated when we develop more things, right? So that's that. And here you see, this is L2 again. These are typically L2 corresponds to functions, but as you know, functions could be functions defined on the real line or any probability space. So a function here is in L2 when it has a finite expectation. In other words, the integral of the function squared is finite. Okay? But again, a forgettable concept for many of you. Daniel, is that clear? Clear, sorry. Does that address your curiosity? You need a full course to make this completely clear. Are we okay, Daniel? Okay, I'm assuming that's a yes. It has to, you're right, it has to do with orthonormal space, but, your real analysis course hasn't done it, don't worry. We're going to deal with that today, but I'm going to give you the finite dimensional version so that when you learn that in your real analysis course, you already know what they're talking about, okay? I'm going to have the intuitive approach to do that. Okay, so market will be complete when the span of a lot is every possible payout. So remove L2 for every possible payout. We already saw this definition earlier, okay? And given any payoff, the price will be a linear function of P, because we know that if I have two different portfolios, the price of one portfolio plus another is the price of one plus the price of the other. So the price is a linear functional. That's how we say that in math. Or is a linear operator. Okay? When I take portfolios are what? In finite dimensions, they are vectors. So the portfolio price is going to be an operator on a vector, which is linear. You probably have seen that if you have linear functions on vectors, they're always matrices. So pricing is going to be multiplication by matrix. We already know that. But if I'm dealing with infinitely many securities or infinitely many events, then the portfolio is a vector, it's really a function in L2. And then we're dealing with a continuous functional, which says functions into functions. And those are not matrices. Matrices are for finite dimensions. Those are called operators. Okay? So I'm trying to speak two languages now. I'm trying to speak the language of finite math that all of you know, and I'm trying to speak the language of infinite dimensional algebra that some of you know, to make that connection. It's worth it, okay? Especially because some of you may actually bump into these terms later, and then I want you to feel powerful because you've already taken a glimpse at that. Okay, so when we deal with infinitely many securities, the price will be a linear, continuous function of the portfolio, and these things are called functional. In the case of finitely many securities, the price is still linear, but then those are called matrices. Okay. And we saw earlier how the price of a security today is something that discounts a future cash flows. We already mentioned the expected discounted payoff. All right, so we're going to develop that we're going to develop the mathematical expression of that, which is called the state price deflator. It's exactly the same thing. It is the way we're going to be calculating the expected discounted payoff. So for every portfolio, we're going to actually show, I'm going to show to you that the price of that portfolio is going to be the expectation of the payoff multiplied by this expected discounted payoff. Now, this is what's interesting here. I'm going to stay with this expression a little bit. The expectation is on the probability given. This could be the wrong probability. Remember when I told you that I had a stock that had a 50% chance of going up and a 50% chance of going down, and then we saw that the price was not 50 cents when I give you $1 if it goes up and 0 if it goes down. We say it's 33 cents. And we explained why, and the reason was a financial reason, because we had replicating portfolios. Then I told you that it's a risk-neutral measure, which is if I give a probability of a third going up and 2/3 going down, then everything works. I can price the security, and by the way, I can also price the stock and the bond. Okay, now I'm expressing that in yet another way, because what I'm saying is that I don't care what probability you give me. A half, fine. I'm going to show you how I can calculate the correct price of the portfolio, in this case the option, by taking expectations against the wrong probability. This is what's interesting. This could be the wrong probability. And you know what I mean by wrong? It's the one that doesn't price the stock or the bond, like 50-50. That was the wrong probability. So what this says is I can always price any portfolio with the wrong probability as long as I do something. I introduce a multiplier here, which has the job of bringing the wrong probability to the right price. We're going to see what this is. For those of you who know math, this is the radon-nicotin derivative between the real-world measure and the risk-neutral measure. If you don't know what the radon-nicotin derivative is, please forget this statement. But if you do, this may be the first time that you've actually seen the radon-nicotin theorem in action. Okay? All right. So the merit of this expression is, as I'm saying, that it prices the portfolio correctly with the wrong probability. And the role of this random variable here is to make the wrong probability give you the right price. It's somehow a fixer. Takes something which is wrong and makes it right. And this is what the state price deflator is. And it's really very related to the vector we saw earlier, which is the one that helps us define the expected discounted payoff. So that's my portfolio vector. That's my payout matrix. And this is the new character in our movie. This is a random variable that is going to have the effect of turning the wrong probability to the right one. I'll give you a preview of what's coming. The use of this is not just that. If it was only that, you say, well, who cares? We already know how to calculate the price. Why do I need this new random variable? Why do I need a new character in this movie? The reason we do is because the properties of this random variable are going to help us understand financial markets. So you just look at this random variable, you can have it in your computer monitor, and for example, it's going to help us it's going to be able to flag when there's an arbitrage opportunity. For example, just like that. I advise you, if this random variable at some point has a component which is negative, there's an arbitrage opportunity, which means leave whatever you're doing, go and find it and make free money. This random variable will have that explanatory power. That's why I want you to know it. Okay? It's amongst other things, not only price derivatives, it's a detector of arbitrage opportunities. So that's what I'm going to do now. Okay? And all right, great. So, another companion of the fundamental theorem of asset management is what I mentioned already 2 weeks ago, which is the efficient market hypothesis, which is there are no arbitrage opportunities. This is what I said, that we're working for free. Everybody works for free for about a few more weeks. Okay? We don't allow making money, and there are no transaction costs. So also there we work for free. So we're in a free trading world for a few more weeks. And now, in this context, the fundamental theorem of asset pricing says that efficient markets have a state price deflator. Moreover, there are no arbitrage opportunities if and only if the state price deflator is always positive. So if at some point it's 0 or negative, there is an arbitrage opportunity. Nice, huh? And if markets are complete, this is a unique function or random variable. Proof. This is the only time in this course that I write this word. Proof. Let me tell you why I'm giving you the proof. I'm giving you the proof not because this proof is important for most of you. In fact, I suspect that none of you will ever use this proof. Never. I'm giving you this proof because I want you to see how advanced mathematics actually found its way into something very topical a few decades ago. So this is for historical reasons. Many of you are mathematicians. Many of you understand proofs. Many of you have been given proofs for breakfast, lunch, and dinner many days. And although I don't do proofs in my course, I want to give you this one. Hard to explain why, but I suspect by the time I'm done, I'll try to do it in less than 15 minutes. And then we take a break. Okay? I think you will understand with me that at the end of that proof, what you have seen was worth it. I don't expect you that you remember this proof. I don't even encourage you to remember this proof. So I would now, if I was you, I would get some popcorn, just watch it. And when it's over, we go have a coffee. But it may be important to watch, okay? And in doing this, I think I'm also going to intentionally try to link it to some other things in math that you may have learned, because I want you to see how things that you may have learned in math may be relevant in this financial context, in different financial contexts. Okay, so I'm going to do the proof in 2 steps. First, I will prove the easy. As you know, if and only if, you always do it in 2 ways, right? So I want to do the easy one. I want to do the easy one, which is I want to prove that if this state price deflector exists and is positive, then there are no arbitrage opportunities. At least that says something interesting already. Oh, by the way, this will be very easy. At least that says something very interesting, because it says that if at some point you have, imagine you have, you have a widget on your computer that just monitors this pi, and if at some point it says, oops, it's negative, like I said, drop what you're doing, leave that meeting, and go do a trade, because you're going to make money. Okay? So that's the first part. We already see something useful there. And then I will prove that pi, if there are no arbitrage opportunities, I'll prove that pi must exist, and it'll be positive, strictly positive. So that's the existence part. It's the least interesting, also the most difficult, but it's going to remind you some of the proofs that you have seen in math, and I thought maybe interesting. Okay, so let me go to the first. Oh, by the way, I'm going to give you a compressed version of this proof. Okay, it's not a formal proof. It's not. If some of you goes and checks the proof of this in a real textbook, which is a bit longer, I'm giving you the compressed version, which is what I really think is worth it for you to know. And I will try to keep it in under 10 minutes. We will see. 10, 15 minutes, that's all. So imagine I have an arbitrage opportunity. An arbitrage opportunity is a portfolio that is expressed like this. Let's go through that. Okay, we've seen this before, but now we have a mathematical expression. What does that mean? That means that the portfolio is going to give us potentially some money. And that means that it's not going to cost us any money. And that means that it's a non-zero probability that it actually will give us strictly money. So this is not that it maybe doesn't give us any money. No. There is a non-zero probability that will give us money. So this is like no cost, maybe even negative cost, a positive payoff, and a chance of gains. Non-zero chance of gain. So for example, if I give you a lottery ticket for free, that's an arbitrage opportunity. It's for free, you don't have to pay. There's 1 in a million chance that you'll make money. That's an arbitrage opportunity. Okay? I'll give you a lottery ticket that maybe, you don't know, maybe it has a 0% chance. I don't know if it has a 0% chance of happening. But imagine that I give you the lottery ticket and I give you some cash. That's an arbitrage opportunity also, because you're making money, right? These are examples. These are arbitrage opportunities. Okay, great. So with that, if there's an arbitrage opportunity, which mathematically is written like this in the language we have developed, since the price of the portfolio, which is the arbitrage opportunity, is the expectation of the portfolio times the random variable times the payout matrix, we'll see that this has to be positive, right? Because the portfolio times that is positive, and this is positive. So this cannot be 0 or negative. You see? You've seen this in calculus, for sure. The integral of a positive function is positive. Cannot be 0 or negative. So that theorem that you saw in calculus, in this context, means that if the state price deflator exists and is positive, then there are no arbitrage opportunities. So you can build your flagging system, your widget. Is this clear? This is the easy one. Are we good with this? Yeah, the faces that I can see tell me that you understand. Daniel is not sure. Daniel is thinking about it. But I think he does. Am I right? Yes. Daniel is thinking of something else that he finds interesting. I don't know what that is. But I think this is understood. And like I said, if somebody says, oh, I don't understand anything and I don't care, that's valid. For this thing, it's okay. Other things in this course, no, but this is okay. All right. So we got this. Yes? Now let me do the hard one, which is if there are no arbitrage opportunities, then the state price deflator must exist and have these properties. Okay? That's the difficult part, but that's the beautiful one. If there are no arbitrage opportunities, this is what I'm going to do. This is a mathematical construction. What I'm going to do is I'm going to create a vector space. It'll be a vector space in finite dimensions. It'll be a Banach space in infinite dimensions, if you know what that means, but it's not important. So I consider a vector space that contains, on the one component, all the possible payoffs. So if my payoffs have dimension m, it has dimension m. And then it's augmented with the cost, with all the price payout combinations, so it's going to have dimension m plus 1. Here it is. It is the vector that contains, is the Cartesian product of all the price payoffs and all the possible payoffs. So this is the payoffs, and that is the costs that my portfolio can have. Okay? I'm going to show you in more detail now. And then inside this vector space, I consider a hyperplane. My hyperplane is this. For every portfolio that exists, I put in the first component the negative of the cost of the portfolio. The portfolio will have a certain cost, so the negative of that goes there. And then on the second, I put the payoff, which is a random variable or a vector. Now, this is a hyperplane inside the big vector space. It has codimension 1. Meaning that in this space, I have many vectors which do not come from portfolios. They're just combinations that no portfolio will give you, but that's okay. That's the definition. The hyperplane is financial. The vector space V is not financial. You've seen hyperplanes and you've seen vector spaces. So here, Q is the cost vector and D is the payout matrix. And now inside this space, inside the space V, I'm going to consider, I have the hyperplane, which is financial. I'm going to consider a cone, which is also financial. The cone is the space where the first component is positive and the second component is positive in all of its components. You know what a cone is? A cone? A cone is not a subspace. A cone is a subset of a vector space that if an element is in it, any positive multiple of it is also in it. A cone. So, for example, you have a cone in R3. I take a certain shape here, and then that's a cone. Okay? Cone. Cone. All right? This is linear algebra. Now, absence of arbitrage implies that the intersection between this cone and the hyperplane is zero. Why? This is a financial statement. Why? Imagine there is something in it. If there is something in it, it has a first positive component, which means it has a negative cost, and all of the payouts are positive in every one of their components. That's an arbitrage opportunity. What I have done here, and this is what's interesting, what I have done here is I've written an arbitrage opportunity as a geometric object in a high dimensional space. One of the reasons I wanted to give you the proof of this theorem. This is mathematical thinking at its best. As a mathematician, you go to this and then you just write your objects, and then suddenly an arbitrage opportunity is a geometric object of the type that you have seen in algebra courses, right? Is this clear? You may have to go through the details of exactly, if this is positive, that means it's negative cost, right? And this is positive in all of its components, that means I never lose money. Oh yeah, it's an arbitrage opportunity. The only thing is zero. Zero is the only one which is allowed to be there. Great. So, by the way, I'm done with the financial considerations. Everything that follows in the proof of this theorem is just math. Because I have a beautiful geometric situation. I have a cone and a hyperplane. And the cone and the hyperplane intersect only at zero. That's my hyperplane, and that's my cone. And they intersect only at zero. It's a mental picture of what I'm dealing with. Okay? All right, now, from here it's only math. This is my aha moment, because if I have a cone and a hyperplane, they all intersect at zero, you may have seen, and if not, I'll tell you now, that there is a linear transformation that sends my entire vector space into the real line, such that the hyperplane goes to zero and the cone goes to the positive real line. Have you seen this? Okay, some of you do not even know what I'm talking about. But let me explain, because you have seen this. In fact, you've seen this even before you knew math. This is the projection on the orthogonal to the hyperplane. A hyperplane has codimension 1. That's your hyperplane. I have the picture there. If I project on the direction which is perpendicular to it, then the hyperplane collapses into zero. But my cone collapses into the positive real line. Now, this is very easy to prove in the case of finite dimension vector spaces. And it's exactly as I told you, is the projection on the orthogonal to the hyperplane. You just prove it. You understand, right? I mean, intuitively it's easy. If you take that vector space and you project on the imagine that my hyperplane is this, is the what's that? The YZ plane. Imagine it's that. And you project on the orthogonal, you project on the x-axis. Then that whole plane goes to zero. And the cone, sorry, that you have to project on there, right? And then, so that whole plane goes to zero, and then it goes into the positive real line. So that's how that works. Now, that's easy to do in the case of finite dimensions. In the case of infinite dimensions, I don't know if you have seen this, this is called the Banach separation theorem. And people who do formal logic will show you that this is equivalent to the axiom of choice. Some of you may know the axiom of choice, some of you don't. But this is interesting because it shows that in infinite dimensions, this map, which is going to be very important to calculate the state price deflator, is something that we cannot build. It cannot be built. It cannot be built. Okay? In finite dimensions, yes. In infinite dimensions, no. Because it's equivalent to the axiom of choice. So that's for those of you who understand what I just said. If you didn't understand that, that's okay. Just ignore. Because that gives me mathematical construction that says that there's a linear transformation that sends my vector space V into exactly this, which is my hyperplane goes to zero, my cone goes to the positive real axis. Now, you may know that every time I have a linear transformation between two linear spaces, in finite dimensions, it has to be a matrix multiplication, or in infinite dimensions, it's going to be given by the, it's going to be given by the, sorry, this is a restatement of what I just said. This is the separating hyperplane theorem. There's a function that sends my vector space to the real line such that the hyperplane goes to zero and the cone goes to the positive real axis. And every such map has to be a vector multiplication, has to be a matrix multiplication, but because we go to dimension 1 to the real line, it has to be a matrix multiplication against the matrix of dimension 1. So it has to be a vector. In infinite dimensions, you have to use the risk representation theorem that some of you may know. It's exactly the same thing. It's the infinite dimensional version of that. Either way, I have a vector, which in my vector space, which contains two components. The first is a number, alpha, and the second is a vector, phi, such that my linear function is given by a dot product against this. So if a function acting on a vector that contains some price element on the first component and some payout element on the second one, this linear functional is the multiplication of the payout times the number alpha times the component-wise multiplication, the dot product between the payout component C and the payout element phi. And I wrote this as that. That's the inner product or the scalar product in Rn. By the way, this would be the inner product in L2 if you do this in infinite dimensions. Okay, great. So with that, now we remember that the inner product is actually a probability expectation because I multiply the components with each other. Therefore, I can rewrite my functional as, I told you this is only mathematical construction. I can rewrite my functional as the product between the price element alpha and the price component V times the expectation of the product between my payout element phi and my payout component C. Since the hyperplane goes to zero, the hyperplane, I remember, was a financial hyperplane, was defined with financial considerations. Therefore, for every portfolio, this equation has to be true because that's how the hyperplane was built. That's exactly what this means when I apply these elements to portfolio payouts and portfolio costs. That's that, and that's that. And now, because of that, I can see that I have found my state price deflator, which is given by the expectation that says that the price of any portfolio is the expectation of this random variable we just calculated, phi divided by alpha, times the payout, the expected payout of the portfolio, and the expectation is with the wrong probability measure. This takes care of turning the wrong probability measure into the right one. And my theorem is proved. This is the fundamental theorem of asset management. Will you ever use this? 99.9% chance no. Is it something which is worth watching once in your life? I think so. It's a very good blueprint for how mathematics is sometimes used to understand complicated objects. And if I was you, what I would walk away with is this representation we made of an arbitrage opportunity as a geometric object, which is the intersection between a cone and a hyperplane. Okay? Good. Okay, I hope this was not too painful. Now I have an example coming up, which I want to go back to the 33-cent game and show you how the 33-cent game fits very, very well within what we just did. But we're going to do that after we take a 10-minute break. So we have seen the fundamental theorem of asset pricing. We have seen the mathematical description, how we deal with financial markets, prices, payouts, arbitrage opportunities even. And we have seen the theory that says that under certain conditions, everything has a price, a unique price. What I want to do now, I want to move away from that, okay? I showed you, it's there for your reference, but let me move away from that. And I'm going to go, for the last time now in this course, for the last time, I'm going to go back to our 33-cent game and express how we would go about the pricing of that situation now from the context of the price deflator, which is the only one that we haven't done. So the question is, what is the state price deflator for our 33-cent game? The market information that we have is zero interest rates, so B equals 1, and a 50% chance for stock moves. The payout matrix is 1, 1, and 2.5, and the cost vector 1, 1. And the payout, the derivative, the call option, for us is going to be a payout which is going to be 1, 0. All right. So according to the fundamental theorem of asset pricing, the price of that portfolio is going to be the expected discounted payoff. Okay, we're going to do, if I apply to the bond, now this is now the bond, okay, if I apply to the bond, 1 bond, 0 stocks, if I apply the state price deflator to that, what I get is at the expectation of my payout, which is 1, and 1 for the bond. Sorry, I made a mistake. There you go. Which is 1 for the bond. That's my state price deflator. That's that, and that's that. That's the same state price deflator, and now what I have is this is that, and this is that. And the 1/2 is, I'm going to do this a different color. The 1/2 is the 1.5% chance is that, and that, and that. Okay, that's all the information that we have. And note, I'm using the wrong probability, 50-50, okay? The one given. So I can see that with that probability, the state price deflator to price the portfolio of the bond only and the portfolio of the stock only correctly, I have to have these two equations work, because that's the value of my bond and that's the value of my stock. So this gives me a system of equations 2 by 2. So I can find the state price deflator by solving the system of equations, and that will give me that the solution is that the state price deflator, the random variable, is equal to 2/3 under the first event and 4/3 under the second event. Note that this is not a probability, it doesn't need to be, it's just the one that prices everything correctly. So this will now price the bond and the stock, and because of the fundamental theorem of asset prices, it's going to price everything correctly. So we can go back to the risk neutral measure and express the risk neutral measure from the point of view of the state price deflator, because as we have here, the price of any portfolio is the expectation with the wrong probability of the payout of the portfolio modified by the state price deflator. Or I can write it mathematically like this, where the expectation of one function according to the wrong probability, to the original probability, is what's given in this expression here, and the expectation with a weight given by pi is this expression here. So this is a notation that is sometimes used in mathematics when I have an expectation with a certain weight. This is called a weight. And then the weight affects the measure that I'm using to calculate the integral or the expectation by multiplying by that random variable. That's the meaning of that. And from here, what I have is that we can express this state price deflator pi as the random negative derivative between the real world measure called P and the risk neutral measure sometimes called Q. So that's another way of expressing this state price deflator, and is the one that affects this, that makes these two expressions be the same. Okay, so again, you may have seen that, maybe not. Okay, we're done. We're done with the 33-cent game. We're done with the fundamental theorem of asset pricing and the conclusion from that. What I want to do now is, I have about an hour left. I want to continue. I want to go to the dynamic asset pricing theory part of that we started also last week, and then finish that by going not just to the part that we did before, but looking at what I call exotic options. And I remind you that when we have the dynamic asset pricing theory framework is one in which I have different time steps for the value of the underlying stock, for example. The approach we're going to take is always going to be the one where which is Markovian, which means going up and down, down and up is the same, or in other words, using recombining trees. We went through that last week. And under that, we saw last week how we can price an option. We went through the example of an option that has a strike price of 75 cents. So as the stock arrives at a value of $1, we'll pay $1.25. When the stock arrives at a price of $1, we'll pay 25 cents. And when the stock arrives at a price of 50 cents, it gives nothing. And we saw how we could price that by backward propagation in that recombining tree. We also saw that last week. So this is not new. This is just what we did last week. Now, I want to now take what we've learned, and I want to move to a financially more complicated situation. If in the first half of today's lecture, I introduce mathematical sophistication, now I'm going to introduce financial sophistication. So imagine the following situation. Imagine I modify this option that we have, call it a game, in such a way that you don't have to wait until the end of time, until the maturity time, to exercise your option. In other words, in this case, I tell you that I give you, I allow you to buy the stock for 75 cents. So whenever the stock is worth anything, you can buy it for 75 cents. Or in other words, I pay you the difference between the value of the stock and 75 cents. And you can do that anytime you want. Now, in this particular game we have here, nothing changes, because the only time at which it would be worthwhile for you to buy the stock for 75 cents is at the expiration, and only if the stock ends up at $1 or $2. Notice that the only other point would be perhaps here buying the stock for 75 cents is something that says, why would you do it? You make 75 cents, and in fact, if you exercise the option at that point to buy a stock, which is $1.50 for 75 cents, give you 75 cents. So would you do it? What's your reaction to that? This is the only, obviously here you're not going to do it because the stock is 75 cents. You will make nothing if you decide to exercise. So this is not a point of discussion. This is the point where I want to discuss with you. If I change the financial conditions for my game and I allow you to buy the stock for 75 cents before expiration, what do you do when the stock rises to $1.50? You have two options. Actually, I'm going to try to avoid the word option and reserve that for derivatives. You have two alternatives. One alternative is you exercise your right, your option, and you can buy the stock, which is $1.50 for 75 cents. In other words, you can pocket 75 cents at this stage. Okay, at this point, you can say exercise. This is not writing. Oh yeah, you can exercise and collect 75 cents. You understand that? I don't think you do. I'll do it again. I want to change the game so that you don't have to wait until maturity to exercise your option. And I allow you to buy the stock for 75 cents at all times. At maturity, you know what that means. I essentially give you something worth $1.25 if the stock is at $2. I give you something which is 25 cents when the stock is $1, or nothing if the stock drops to 50 cents. But if you go before that, and I allow you to buy the stock for 75 cents before maturity, what would you do? And the question I'm addressing is, in this particular case here, when the stock is $1.50, would you exercise your right? Would you buy the stock for 75 cents? In other words, this looks like gambling now, because if you are here and you exercise, I have this written down in the next slide, okay? But I'm still going to write it with my hand because I want to make sure that everything is understood before I go to the next slide. So if you exercise, you make 75 cents because you can buy the stock, which is $1.50, for 75 cents. But if you wait, you have uncertainty. You can make more, you can make less. You can make $1.25, you can make 25 cents. What shall you do? That's the question I want to address. That's here. Let me go to this note here. What do you do here? You could buy the stock now for 75 cents and make 25 cents profit. Would you wait? If you wait, you can make more money. You can also lose more money. What do you do? So again, it looks like gambling. And we've learned now that these things that look like gambling, maybe they're not gambling. In fact, finance is usually not gambling. So how does this work? And this is something different. This is something we haven't seen before. I call it exotic because we're starting to now value not securities, but decisions. And this is something that happens in finance all the time. So I'm going to use this example as a way to understand that. And this is the way we think about that. We have the payout at maturity at my last column. And then I have this, if you have to wait to collect that, this is what a European call is. They're called European, no particular geopolitical meaning here in this term. They're just called European. Can you exercise early? Is it worthwhile for you to exercise early? So this is how you think about that in an organized way. If you're given the opportunity to exercise early, the way you think about that is you're always going to be comparing the to be or not to be, the to do or not to do. You're always going to say, what's the price if I do this? What is the price if I do that? Then you take the price which is best for you, and that is how you're going to make decisions. So very, very simple. We're going to price decisions by understanding the price under every scenario or under every decision that we have to make. And there, we're going to now be confronted with, in this case, only two decisions, to do or not to do. If you don't do, is what we call European, you just wait. And if you do, we're going to call that American. And no geopolitical implications from this, from these terms. This is just the way these things are called in finance. So let me go through this in some detail. And I'm going to focus on the point where it is, I guess, most interesting to look at. And perhaps there's only 2 points here where the answer is non-trivial. Okay? It's this and right now at the very beginning. Let me focus on that. How do we decide if we exercise the option when the stock is $1.50? In other words, shall we take a bird in our hand of 75 cents or shall we continue to play this game of $1.25 and 25 cents? And as you will see, gambling is not the issue here. The way we think about that is as follows. We look at that part of the recombining tree, and then we think, if I exercise, I collect 25 cents. I get my payoff at that point in time, I collect my 25 cents. So exercising gives me 75 cents. That's clear. And then I don't care what happens with the stock after because I've lost my option. My option is now exercised. I don't have it anymore. If I don't exercise, what happens is that I have a European branch and I know the value of not exercising. I know. And it's not that I'm gambling. We went through that already last week. We're not gambling. The value of not exercising is the value of the European branch. That happens to be 75 cents. So in this case, I'm indifferent because exercising gives me 75 cents and not exercising gives me an option which is also worth 75 cents. So this is what is called a point of indifference. Okay? But that gives us an algorithm to make decisions whether to exercise or not to exercise. And the algorithm is this. The way we're going to decide whether we exercise or not is we're going to look at the price with exercise and the price without exercise. The price with exercise is always cash, S minus K. And the price without exercise is the price of a European option, which we already know how to calculate. So we just look at those and we take whatever is best for us. We take whichever is bigger. That's the algorithm to make decisions. We calculate both and we decide. So this is easy. And this is how American options are priced, and that's all the time I want to spend on American options, and there's a big literature on that. But now, financially, this is interesting, the pricing of a decision, but it's very easy. I want to make it more complicated. As I mentioned to you today, I want to increase the financial complexity, perhaps as much or even more as I increase the mathematical complexity in the first half of this lecture today. And for that, I want to introduce the concept of a swing option. These are options which have been traded for decades. They're very interesting, and they are very relevant for what we're talking about here today. So they have different names: swing contracts, take and pay options, variable, base load, factor contracts, flexi caps. They have many different names. And they were developed for commodity markets: electricity, oil, natural gas. These are markets, as you will see, markets that have volumetric constraints. When you buy stock, buying one stock or a million stocks is essentially the same. You just write a bigger check. But if you're buying a megawatt of electricity or 1,000 megawatts of electricity, it makes a very big difference, because this is something which it has to be consumed very quickly, right? And same if you buy oil or natural gas or anything that requires storage. Stocks do not really require storage. They say, essentially, they don't. So what happens in those situations? So these markets developed, and there's a way of thinking about them, which is what I want to address now. I want to show you how powerful we are, how we have developed these superpowers to the point that we can deal even with situations where we're dealing with physical objects that may require additional considerations, such as, for example, storage or consumption in the case of electricity. And these have been used as hedging as hedging instruments against prices going up and going down. Airlines, for example, they use things such as this, and I'm going to use airlines today as an example. Okay, so anything that has a volumetric constraint is going to be of interest to us. But I want to do it in the context of something I find very cute, very, very nice, and it is the concept of an Air Canada flight pass. I don't know if you know these flight passes. I don't know. I used to buy them a decade. I used to go to New York every month, several times, sometimes. So not to be subject to the fluctuations of prices, Air Canada gives you the ability to buy a flight pass. And the flight pass, I don't know if this is current. These prices are probably old. It doesn't matter. It doesn't matter to us. But what Air Canada does is they give you the opportunity to buy tickets in advance. Somehow you prepay. And then you have the option to go, and the price is now guaranteed. I'm not going to get into the legality, the legal aspects of this. I bought these for many, many years. The last time I bought them, I was very upset with Air Canada, very upset, because you buy these flight passes, and then you're stuck with a particular fare class. Like, you can't go in a different fare class, even if you're willing to pay the difference. And I was not aware of that. And sometimes they have, and it's not economy business, or no, it's a fare class, something that only they control. So I was very upset that I have this information asymmetry, and I never bought these flight passes again. But ignoring that for the lecture today, ignoring that, I'm going to assume that these are just tickets that allow you to fly without looking at the fine print or the particular details of that. So we can see here that if we want to, for example, you want to fly, this is the New York-Boston commuter. That's the one I used to buy. So if you buy 8 flight credits, you pay $2,000, roughly, which amounts to paying, $300 per segment. It's pretty good. Sometimes you can get cheaper, but oftentimes you're going to be more expensive than that. So I guess Air Canada thinks it's a good deal for them if people buy 8 flight credits, and some people think it's a good deal for them if they pay $2,169 for that. As I was one of them at some point. Okay, that's if you buy 8. You can buy And you can buy more, 10, you can choose different classes of fare. I'm not interested in that. I'm only interested in that. How many? I'm only interested in that. And let's say I want to pick 10. 10 is a nice number, better than 8. And, sorry, yes, okay. So I'm going to do 10, which means that essentially I'm paying $382 per segment. Okay? All right. That's the one that I'm going to be focusing on. That's the easy one. $382 per segment. Actually, this is a mistake. You cannot fly. It's 10 times, not 8 times. I made a mistake there. Okay? It's 10 times. You can fly 10 times whenever there's in a 1 year period, and you pay $382 per trip. The reason I made that mistake is because the price for 8 is exactly the same, and I guess I changed my mind which one I was going to talk about. Okay, it's 10 times. All right. The key here is you cannot fly twice in the same flight. That's the thing. See, let's think about this financially. Imagine I could fly twice in the same flight. And imagine that I have 10 of those tickets. Then if at some point it's optimal for me, because prices are expensive, to exercise this option, then I would not exercise only one, I would exercise all 10. Okay, let's think about that in a different way. Imagine that instead of this, imagine that it's not a ticket, it's not an air ticket. It's a stock. I can buy stock for $382. And I bought the right to buy 10 of those stocks for $3,822. And we go through the decision that we just saw earlier, and we say, oh, today is the time for me to exercise. Exercise is what I should do. And if that's the case, you don't exercise only one, you exercise all 10. Why would you exercise only one? If it's optimal for one, it's optimal for 10. So when you look at American options, the idea is that it doesn't matter how many of them you have, you exercise all of them at the same time. But if you have this situation, you don't. You can only fly once with that book of tickets. If you decide to fly, you only exercise one. This is relevant because I give you another example where this happened. It may be easier to understand. I assume some of you have a car, and I assume some of you buy for your own gasoline. Imagine I give you the following contract. I'm going to allow you. I'm going to sell you a contract that for the next year, you can buy gasoline at a fixed price. I say I'm going to charge you $1.30 per liter for the next year. But we have to agree how many liters you want to buy protection for. Let's say, I'm just making these numbers up. Let's say you buy 1,000 liters. So you pay me $1,300. And sorry, you don't pay me $1,300. Yes, you pay me $1,300, and that means that you can buy gasoline. You can get 1,000 liters whenever you want. How do you decide when you go to your car? If one day gasoline is at $2, you say, well, and imagine that you go through a decision process like we saw here and say, well, this is it's optimal for me today with market prices what they are. It's optimal for me to exercise. You can only exercise whatever fits in your tank in the car. What are you going to do with the rest, right? And the same thing applies to natural gas, oil, electricity. anything, any commodity that has some sort of a constraint, air tickets, they would typically be traded as swing options. They will not be traded as American options. Why? If Air Canada is going to sell me a 10 flight pass that I could exercise all 10 in the same flight, it's going to be more expensive. Why? Because I have more freedom. Every time I have more freedom, I pay more. If I introduce constraints into what I'm doing, I pay less. This is a concept which goes back to insurance. Imagine that I sell you car insurance with the condition that you never drive on weekends. Then of course the insurance will be cheaper because you're giving up rights. So every time you give up rights, you get a cheaper insurance. Every time you have more conditions on your purchase, you're going to pay less. And that's why in the case of air tickets, since no one in their right mind would fly even twice to New York on the same day, if I give you the restriction that you can only fly once to New York on a given day, then that contributes to making the price cheaper. So everybody's happy. And that's why these things are sold like that. Okay? So this is the finance of that. There's different versions of that with the small and medium-sized companies, which actually you can fly 10 employees, so you could sell 10 tickets on the same flight. But we're not going to look into that. I just want to give you an idea of the type of sophistication financial markets have. And what we have learned here is not only used for financial derivatives, it's used for what's called real options. For situations where you're dealing with real assets that you want to buy and sell, that will have that will have the ability to make you decide what you do. Okay, so we're going to be making a very difficult decision, which is I'm going to have a situation where I need to decide if I take one of these tickets or not. Okay, now I'm not going to do it in the case of tickets with Air Canada. This is a little bit difficult. You know, it's what I'm going to do is I'm going to do it in the case of the stocks that we have seen before. So I'm going to focus on the same example we have seen, but now I'm going to allow you to do 2 trades. I'm going to sell you 2 options. You can buy 2 stocks for 75 cents, just not on the same day. That's going to be an easy enough example to understand. I'm going to give you 2 stocks, 2 options that you can buy stocks, but you cannot exercise it on the same day. We know the price of one option. The price of this new contract is going to be less than twice that price. Okay, so that's my payoff. You can exercise, if you can exercise twice, then we'll pay twice as much. But if I say not on the same day, then your rights are less, so this should be cheaper. What's the price? What's the price of this new option I just made up for you, trying to mimic the flight passes or the flexi caps or the contracts on energy, oil, or gasoline? By the way, the contract that I gave you, the price protection contract I gave you for gasoline, you can actually buy it from Exxon. I don't know if they still sell it, but at some point they actually had it. You could sign up and pay them some money, and they give you that. So we are surrounded by things like this. And I want to use this as a good example to understand a very sophisticated financial situation where our discipline, math thinking, holds the key to understand what's going on. So I'm going to be focused on pricing this security, which is 2 options that cannot be exercised on the same day. I call it P2. Some very simple reflection, at least it's going to be 25 cents. The price of that is going to be at least 25 cents. Why? Well, there are many reasons that you can conclude that. Because I can exercise one right now, and that's going to give me 25 cents. So the price has to be at least 25 cents. It can be no more than $1. In fact, it can be no more than 66 cents. because if I complete the option payout, which we already did last week, we see that it's 33 cents. So it's a third, right? Since we already saw that this has to be cheaper than two of these options, the price cannot be more than 2/3. So that is a very nice upper and lower bound, but we're not interested in upper and lower bound. We want to know what the price is. These are just some considerations to make sure that you understand the financial security I created today. Is this clear? It's two options, but you can only exercise one on a given day. There's 3 days, so you can exercise one today, in which case you have one left. Then if you exercise tomorrow, you're done. But if you don't exercise today, you can exercise tomorrow, and then at maturity, this is the set. Very small set, very simple example. But we're going to develop the way of thinking that will work whether I have 300 days and 300 or 10 flight passes. It doesn't matter. The way of thinking we're going to develop will work for any amount of options we're dealing with, or exercise limitations we're dealing with. Okay? Are you ready? I'm not going to teach you anything new. Everything we're going to do now is something we've already seen. We're just going to put everything into a logical sequence that will get us to the right answer. But we have to think financially. Okay? So let's see. I'm going to start. I want to see if I can get it done. The basic decision is to exercise or not to exercise. And we're always going to do the same. If we exercise, we typically know how much money that means. In the case of the American option, exercise would give us some cash. But if I have a ticket, so if I have a book of 2 tickets, if I exercise, I not only get some cash. What do I get? I get some cash and a book of 1 ticket left that I could exercise in the future. And that's what I call P1, 1.51. Okay, let's go through this. This is a book of 1 ticket. This is now an American option. It's a book of 1 ticket left. There's 1 ticket left. This is the value of the stock, in this case at that point in time. And maybe I go to the previous slide, because this is why I introduce the notation. Just make sure that we understand what we're doing. Okay, we call this how many tickets, the value of the stock. This is when. So 0, 1, 2. Okay, so with that, I get 75 cents plus a book of 1 ticket when the stock is 150 at time 1. That's the value if I exercise. Everybody understands that? $0.75 is my payout, but then I have a ticket left. If I have a book of 10 tickets, the first time I exercise one of them and I go to New York, I get some payment, some savings, and then I have a book of 9 tickets left. It's always 1 less. Okay? This is the finance. I just need you, there's no math here. This is just the finance. We just need to understand the finance here. That is an American option. So we know how to price that. We saw that earlier today. If we don't exercise, however, what I have is a gold American option. I collect no payment and I just price the option by pricing the option like the 33-cent gain. So it's a European branch. my option will be worth $1.25 or 25 cents. Therefore, the value of that is 75 cents today. If I don't exercise, 75 cents. So clearly, what do I do? It's 75 cents, by the way, because when I go to maturity, I can only exercise one. Although I have 2 tickets left, I can only exercise one. So if I don't exercise, what I get is a European option. If I don't exercise, what I get is $1.50 if I exercise, and if I don't exercise, it's 75 cents. So clearly what I do is I exercise. This is common sense. I mean, I'm trying to do math here for something which is common sense, but the algorithm is what I want you to understand. The algorithm will work when I have no common sense. The common sense is that I have 2 tickets left and only 2 days left. Of course I take it. But that's not the way we think, because that will only work in obvious cases. In cases where it's not obvious, we don't know what to do. Okay? So I'm not following the obvious path, which only happens to work in this particular case. I'm trying to explain the algorithm to you. And the algorithm is, if you exercise, you always have some cash and some other security. That's what's different about these options. It's not just cash, what you get when you exercise. You also get another security. If you don't exercise, you already know what you will get paid. So it's a European branch, and the value is the one that you calculate with risk-neutral measures, for example, which we already saw. So here it's clear, we exercise, but not because of common sense. I have an algorithm that tells me that I should exercise. So the price of, in this case, a 2-up swing option or a K-up swing option, it's cheaper than the price of the corresponding number of vetted options. And we always exercise when the difference between the payout and the payout plus the other security I'm given is more than if I don't. Or in other words, the difference between the 2-up price and the 1-up price is less than the cash I get. Okay, that's the algorithm that we're following. So if we have a tree like that, the way to express that is as follows. In the case, so we already saw in the case of the node when S is 1, when here we already saw that when the underlying is 1. Let's go to the case down here. What happens here? Here the stock is 75 cents. So exercising or not exercising is really the same to me. I already have the flight pass. So exercising or not is the same to me, because the payout is 0. And then I have a book of 1 ticket left that I may exercise at the end. So in this case, the algorithm will say that whether you exercise or not, you're indifferent to that. So this is a point of indifference. Let's go here. This is the interesting place. What do I do now? I just bought my flight pass and I'm going to New York. And I have the ability to exercise now or wait. So what do I do? If I exercise now, I value the American option, which will give me 33 cents. That's the number I have from earlier. That's the value of the American option. And the value of my swing option, and the payout for my swing option is 75 cents minus $1, which is 25 cents. So if I exercise now, I have 25 cents plus a third, which is 58 cents and a third. That's if I exercise. $0.58 and a third. That's if I exercise. If I don't exercise, what do I have? Well, I have a European branch that gives me $1.50 or 12 and a half. And I calculate that the value of that is going to be, it happens to be the same, 58 and a third. Just this is the replicated portfolio that gives me that. So this would be another point of indifference. Okay. The interesting thing here is that, let's say I don't have it written, but imagine that I had a, not just 3 days, but many days, 100 days, and I have a book of 3 tickets. Every time, the way the algorithm works is every time I need to make a decision, I calculate the value if I exercise, which is some payout and a new security, or the value if I don't exercise, which is always going to be a European branch, which we already know how to do. And you always compare. And you always take what gives you the highest payoff. And that's how you decide if you exercise, which means collect some cash and change trees, a tree that you can build recursively because each tree contains one option less, so you've done it already. You start, it's backward propagation in time, but it's also backward propagation in the number of contracts left. You start with, actually it's forward propagation in the number of contracts left. You start with 1, that's the American option. Then you go to 2, is the 2 upswing, for which you need the 1 option left, which is the American option. Then you go to 3, and when you exercise, you jump trees to the book of tickets that has 2. Then you go to 4. Every time you exercise, you jump to the 3 with 3 tickets that you've already priced. Then you go to 5, 6, until you get to 10. So it's backward propagation in time, and it's forward propagation in the number of tickets left. And this is perhaps the most sophisticated derivative that you can imagine. And now you can price it. It is, I know how hard this is, okay? And I am fully aware that you didn't understand everything I said. You're right, David. It's very like recursible. Yes, it does. But there's more. I'm also aware that I lied a little bit to you. Because at this point, I'm not interested that you know the actual exact algorithm to price this. My objective is not that you become expert price producers of swing options. It's that you understand how powerful you have become, like Hercules. There's still some work left, which I'm not going to do, okay? I just want that window to be open so you can see what's out there. And I want you to feel that you can actually just go and grab it if you ever have to. I think every financial derivative that you will encounter, a Bermudan option, things, is going to look very much like in all of these things that we have done, which are fairly, I mean, we've managed in 2 weeks to cover a lot of ground. So my objective is that you feel powerful, not that you understand what I've told you today. I need you to understand everything we discussed last week. But as I mentioned today, I just want you to feel powerful. I want you to see all the things that we can do. If we spend more time on this, then it'll be easier. There's one thing I hid under the rug, which will make things a bit more complicated. But it will not lead to an interesting educational discussion today. Okay, so I will end the way I started. The class today was designed so you get to see the landscapes which exist in mountains we're not going to climb. We have developed, I think, a very solid foundation with the capital asset pricing model and the dynamic asset pricing theory, from which we can see far. And we can see many things that we could do if we wanted to. And I believe that you are equipped with enough technical knowledge that if you ever have to go to those landscapes, you can actually do well. I'm going to leave that now. So next week, I will explain to you some math first, because you may not know, I assume you do not know stochastic analysis. So that's what I will do next week. I'll start with stochastic analysis. I'll make you more mathematically powerful first. So I want to talk about probability, I want to talk about random walks, about the central limit theorem, and this and that. And once we have that, I will develop the theory of continuous time pricing. I will do the Black-Scholes theory, and then I will use that to give you a glimpse of how these things that we've learned today in greater generality are used in financial markets. And by that time, I think you have a pretty good knowledge, very solid knowledge of how many financial instruments work. That's going to take us 2 weeks. 1 week for the math and 1 week for the finance. And at the end of that, we'll be finished with that finance. And then I'll move into risk management, the area where I suspect many of you will be getting jobs. And at the end of that, I will get into investments, where still some of you will be getting jobs, especially in Toronto, a very strong capital for investing. And then we do our communication skills session followed by dinner, and that'll be the end of the course.